I think we got Ignacio on now.
Yeah, that's correct.
Yeah, hello.
Hey. Welcome.
And Richard.
Hi.
Hey, Richard.
Oh,
you
Richard
doing?
too. Awesome.
On a Sunday. Nice.
Hi. So, for the best, we were just shooting the breeze, as it were, talking about Eugene's upcoming thing, a little bit of stuff with the Doherty set, and while we waited for you to get on, unfortunately, Dave's computer just committed Harry-Carry, and so as he deals with its ritual suicide, we will have to continue.
That would have been
without him.
Honorable. I don't find there is no honor in this.
There is no honor in this show. But yes, so I know that Eugene and Heather and a few others have been talking to you, Ignacio. I saw the feed just pop up with all this other stuff. So I'm very happy to have you on. We haven't had a chance to I really this was all kind of impromptu, so I'm just happy that it's happening. So but as you might know some people here, I'm obviously Neil Thompson. We met at 2016. We had a few chats there. Obviously, I don't know if you know Jim Winiger.
By name?
By name only, by reputation.
Yes.
We have Robert Hawthorne, Jr. and Sr. under RH there. Of course, you know Eugene, Buddy James. He's a big thing with the Doherty set going on. Does a lot of stuff in the EU, really. With Heather, works with a lot of the artistry stuff with it inside the background and stuff like that. Richard, as we know, author and just all-around cool guy who loves hats. And that was it. And then, of course, there's me. So, yeah, there, we've done the introductions. Welcome to the December 16th edition of the Electric View. I'm Neil Thompson. Today we have Jim, Robert, Heather, Buddy, Eugene, Richard, and our special guest, Ignacio Cisneros. We are delving into Ignacio's work in plasma cosmology and astrophysics, and gleaning what he has learned about our dynamic sky. Please take a moment to like and subscribe.
Okay, so I just wanted to ask Ignacio.
Keep sharing, Heather.
Ignacio, can you tell us a little bit more about your background? You obviously have a lot of experience in working with, imagery from astronomical observatory.
Okay, so let me describe a little bit of how I got here and where I am.
Perfect.
Curiously, I started out 30 years ago in the arts, painting and sculpture, and I moved into digital imagery because I was working in television. It wasn't until my 30s that I got involved in astronomy. It was also the time where the internet was coming online and astronomy was migrating into the internet. So I applied my imaging skills to observing the DSS and then later the IRIS data set, which is optical and infrared data sets, all sky survey. There's a service in NASA called Skyview. As Skyview grew and offered more and more wavelengths to study the sky in, I increased my knowledge. So about 2012 to 2013, I was enormously frustrated. Let me have to go back a little bit. When I got into astronomy for real, I went back to college and I started studying star formation. And so I approach astronomy through star formation and the study of H2 regions and giant molecular clouds. That's how I entered the literature, looking for a understanding of the star formation theory, vintage 1990 to 2000. Pretty much all the papers I was reading in about 2000, 2005 were from the late 20th century. In 2010, the whole community received the high-resolution infrared survey called the WISE survey, Wide Area Infrared Survey. That superseded the IRIS. And it gave us a whole new look at what was happening inside molecular clouds. Why is this important? because molecular clouds are said to be the nesting or the birthplace of O and B type stars. And star formation was presented to the world as a gravitational collapse of these molecular clouds into high mass stars. No one had yet understood how low mass stars were to be formed under these conditions, but they thought they had an idea about, had a solution for how O and B stars were formed. That's where I get in and start looking at the galactic panorama. And for the life of me back then in 2012 through 2014, I could not justify the shape of the interstellar medium, the shape of the H2 regions, by processes that were part of the mainstream's ideology. Supernovas alone, pushing dust around, couldn't justify the general shape of the interstellar medium. And ultimately, why does it have any shape at all? Why is the dust held together in any form? That is really the most interesting question. Okay, so when I met the EU, I realized that there was another form of energy that might be shaping the galaxy, shaping the dust around the galaxy. I couldn't do it through mechanical, explosive, thermodynamic principles. It didn't add up. But if you thought of the interstellar medium as conducting electricity, and that this was the force that was shaping the ISM, everything kind of fell into its own place. The galactic panorama appeared to be much more cohesive in terms of its shape. So then the proposition that the solar system as we see it today was a consequence of the merger of a small star and a large star, that was Thornhill's idea, that this merger was the origin of the odd morphology of the solar system. I decided to test that hypothesis. I went in and started looking for brown dwarfs and started trying to understand as much as I could about brown dwarfs. This is a time when brown dwarfs were very popular. They still are, but they had a sort of moment in the sun in the mainstream academic community. They were beginning to be found more often. They were theoretical at first, then they began to be found, then their atmospheres began to be studied spectroscopically. So we had literature about brown dwarfs. In looking for brown dwarfs, I had to do blink comparison between epochs. I had to compare the 1950s DSS from the 1990s DSS to see if I could find close by molecular clouds that held brown dwarfs. In doing so, I realized that there was more motion in the interstellar medium that was accounted for in the literature. Just was more stuff happening. Amongst that, I call it signal that resembled discharge plasma. It resembled lightning. Not just the dark clouds and filaments moving around. It's not just tiny stars attached to tails that then are attached to the giant molecular clouds. It also seems to be plasma discharge. So that's where I concentrated my efforts in resurveying a great many H2 regions. That's how they're known in astronomy, because they have single and doubly ionized hydrogen, and they typically are right up and against the clouds, and the H2 regions is kind of a synonym to star formation region. Now, star formation region and H2 are mainstream parlance because they only see a gravitational implosion, radiative gravitational implosion mechanism for star formation. And so that's how it all appears in the literature. I'm trying to figure out what is all of this stuff. Can you stop there at that picture? That's a nice one to look at, the general galactic panorama. These dark molecular clouds are often surrounded by ionized materials, bubbles of plasma, and they often are interconnected amongst themselves. You'll find a filament running from one to the other, to the other, to the other, and this is what makes up the dusty backbone, or that's not a backbone, but the dusty lanes in the galactic plane can be seen as spiral arms in external galaxies. That's what they're composed of. Or that's how they appear. We do not know exactly what they're composed of. Most of the stuff that is detected there is molecular hydrogen, carbon monoxide, and dust. And a lot of the interstellar medium studies revolves around dust. Dust in the form of silicates that are covered by ices, and a great variety of organic molecules, polycyclic aromatic molecules are found in copious numbers. So all that dark stuff is probably dark because of its sooty molecular content. If one goes and one study, if you go into material science right now and you look at the darkest materials you can find, it's always going to be a forest of nanotubes. You have a surface, you can grow a forest or a thicket of nanotubes. On top of that, a few microns thick, and that material becomes the darkest material you can find. It just absorbs everything. All the photons just crash into it, and you don't see anything. It absorbs everything. These dark molecular cores that you see here are just like that. They're very dark. They're very, very cold. And they harbor these cores, these we call embedded sources that are bright in the infrared. And that is what today we think of as nascent or protostellar objects. They're there. It's yet to. I don't know how it happens. I think I would be correct to say it's yet to understand. We have yet to understand how the magnetic fields in these places wrap up around themselves and create these filamentary structures.
Yeah, we haven't seen proof of that yet. Yeah, like we have some good theories, but
that's correct, and I have some okay theories. Maybe
I think
notions.
We're on the same page. There's some notions, yeah, some feelings,
notions about it,
but I couldn't turn it into a formula. No.
Okay, well,
I mean, have you seen Don Scott's thing on Berkeley currents?
Yeah, sure, I have, and that seems to apply more. How can I say? It's more visible in the atmosphere of Jupiter. If you look down on Jupiter, for instance, and you see these banded things,
yeah,
that seems to be just like Scott is describing, that the Berkeley current and the counter rotation, and so the planet is a knot in some great current.
Similar to the sun, as we see some banding there too, counter rotation, et cetera, et cetera.
Yeah, there we go. But someone's got to fly a bunch of magnetometers or voltmeters in that direction. Okay, so that's
it would be quite a web of them.
What I've done.
But yeah,
just to conclude, and I'll be quiet in a bit.
No, please. I was mesmerized.
Well, that's the synopsis of where I came from, how I got here, and what I've been doing. Everything else is we can talk about details. And there's some other things too, but yeah.
That's quite the direction.
I've heard of dark magnetic cores, and someone was trying to say something along the lines of our iris and our eyes might be something like a dark magnetic core. I'm not sure the correlation.
Dark magnetic core, like molecular cores.
It was a passing by comment that someone had made, and it just reminds me of like connecting black holes to your iris, and like it's the absence of light. If you look at your not your iris, your pupil.
Oh well, okay. Well, that's very poetic, but I don't think it's applicable. I think that the most interesting thing we have now is the Planck spacecraft, which was a cosmological mission, had to measure the galactic dust very carefully so they could subtract it from their attempt of measuring the background radiation. Okay. The Planck spacecraft produced a polarization map. And polarization studies is what mainstream science uses to determine magnetic fields. It's an indirect form. Planck polarization map. Galactic polarization map. It's a very nice image in general. It looks like it was done by a Zen gardener. See what that pulls up. Okay, there it is. Okay, so just take the upper left-hand corner and blow that up. Okay, so this is the closest, highest resolution thing, or the highest resolution, closest presentation of the galactic magnetic field. This is really important. Although I could not validate, or I cannot validate how they arrived at this particular shape of it, meaning that I haven't studied the instrument or that particular chapter in the Planck consortium publications that deals with the polarization map. Basically, what they suggest is that these grains are not symmetrical, they're elongated, and these dust grains then become aligned to the magnetic field, and this polarizes the radiation so they can infer the magnetic field from the polarization caused by the dust. That's kind of the theory of how this map exists in a nutshell, right? So if you go back to, if you scroll down to the image that's right below it, like that one right there. Okay, that's the one just above that shows the Taurus molecular cloud. Right here it says Planck highlights. The one that's just above or just below. No, just above. This one. That one, yeah, the one you have your finger on. That one. That one, yes, exactly that one. Okay. This shows the Taurus molecular cloud, which is the typical place astronomers look for evidence of star formation. It's one of the closest star formations to it. If you've ever seen the EU present images of long filamentary structures that were captured by the ALMA radio telescope, that's here. That's exactly here. Okay. If you look in the corner of this image, you're going to see a little knot right there. That little knot is a isolated molecular cloud. And in that knot, there are some extraordinary events, HH objects, Harbig-Haro objects. This is a place where big jets and long arching filaments can be seen coming from protostellar objects.
Right.
That is there. So that's an example of a place that you would go to study. You would do blink comparisons there. You go to see how much the interstellar medium changed and how you can wrap any form of measurement around that particular cloud to try to establish a connection between the perceived or measured magnetic field, indirectly measured magnetic field, and whatever electrical activity you intend to establish or prove. That would be an example of it because it's isolated, because it has tremendous activity, and there's like Hubble Space Telescopes of that object right there, of the core really active areas, and because it's obvious that the entire cloud has a different magnetic field than the background. And you can see the background is blue and in one direction, and the molecular core there, or the molecular cloud there, has its own. Okay. There's also a very large red star that might be associated with that molecular cloud. So it has all of the ingredients to go and say, well, if we can establish in normal astronomy how much matter should be there. We can try to establish how much energy is being sputtered off in the so-called star formation regions, and we can try to connect the molecular cloud to the nearby stars thanks to the Gaia telescope and its parallax measurements. That's the kind of stuff that I would do today to try to advance the cause forward, would be to look at that specifically. And I have. But, doing the physics, I'm good at combining the images and looking across wavelengths. I have lots of experience in the morphology of the ISM. I've seen it all. I know what's going to be a blemish or a signal or a transient or whatever it is. I've seen it before. What I'm not good at is doing the equations and doing the actual physics. I am not a physicist. I am an astronomer. I'll tell you how bright, how big, and how far it is, but how hot and how heavy and how fast, that's the astrophysical side of things. That's the physics side of things. And I think it's very important to distinguish that, what astronomy is and what the physicists do with the astronomy. And then there is the plasma physicists. The plasma people have to have their own sort of nutshell occupation. How bright, how far, and how big for the astronomers, how hot, how heavy, and how fast for the physicists. And I don't know what the plasma guys would have to say. It's probably more than 3. Like what is the voltage of it, the electron content, what is the plasma density, plasma temperature, that kind of thing. But okay, that's that comment. I'll be quiet now.
So you're sounds like you're really into the sort of our side of the fence, the electric universe understanding. But are you still able to be a recognized astronomer and publish in astronomy journals?
Well, not by myself. I got published this summer. Some guy at Dartmouth was doing supernova remnant studies, and he asked me about to provide an image for him. And so I provided images using a variety of wavelengths that described the Cygnus loop physically, and I got published as a co-author on that paper.
That's cool.
But I don't usually publish in the mainstream. I usually just lurk around the shadows. See, this is the thing. This is kind of the most interesting map that you're seeing right here. This is one of the first maps that ESA released. And it doesn't have the coloration, so the chromaticity that the other one has. And you can really begin to kind of sense what the magnetic field is like in the galaxy. But I don't know how faithful it is. Like, I couldn't validate how they actually got to this point, these guys with the Planck Consortium, but I think it's one of the most relevant advancements in astronomy and astrophysics to the EU thing. Mostly because, you see, from my point of view, astronomers do not understand how stars form. And if you don't understand how stars form... Excuse me?
I said, or work, or... No.
Well, let's just say that because they think they know how they work, they have a very fixed idea of how they should form. You see?
Of course, yes.
And
evolve.
And evolve. That's correct. So the consequence of this is they really don't know how galaxies form. Right? And if you don't know how galaxy forms, any grand perspective of cosmology doesn't bear any weight. You can't have a cosmology if you don't understand your star. And if you don't understand your star, you don't understand how the galaxy really runs. And I think that's the boat in which we are all in. The problem I see is that there may be many different types of stars. if we move away from the gravity and gravitational pressure and nuclear fusion set of stars to an external energy source for the photosphere and the chromosphere, then you got to go look out in the galaxy and find out, well, how do stars in other environments behave? Like really dusty environments are very different than clean environments. They must behave differently. And that brings us to this idea of complex plasma or dusty plasma. Now, that's a very hot topic these days, but it's a topic that's not well developed. When you look at literature for dusty plasma, complex plasma, you see people with a vacuum bell making grains of sand bounce around. That's how primitive the experiments are.
That's fairly primitive, yeah.
Yeah, it's very primitive. When you get to the interstellar medium, you have huge areas, huge, large, astronomically big spaces that are dusty. And it's not understood how this, quote, doped plasma behaves. Or
that's a neat term to use, by the way.
It is, because
it implies a diode.
That's correct. And so when you look at the little grains of sand that tend to be silicate cores with a shell of ice around them, and you imagine these things spread at a density of, say, 10 to the third, 10 to the fourth particles per cubic centimeter, we don't quite understand. Our society, our civilization doesn't understand what the behavior of plasma is at those scales.
No, it's actually very hard to visualize. I mean, I can put it in my head and say, okay, well, let's just scale up what I see in the laboratory or what I see in Thunderball videos, with those twisting little bands of current going from the one glass to the other part of the glass, but that's only if the VI curve is at this much. If the VI curve goes to here, if the density changes to this, all of the characteristics are just different.
So, what we do see in the interstellar medium, in these denser regions, you go back up to the the Rho-Fucus images. There were several of them high up. That's also extragalactic. That's extragalactic. They were amongst the first ones. Yeah, that's another question.
Chop, Heather. Come on. Sorry.
Oh, that's Heather doing this.
My computer doesn't do what I tell it.
No. I am being a jerk. Don't even think about apologizing. You should just tell me right off.
Okay, one of these will be good. Like this one, okay? This one's fine. That's great. Well, okay. So what happens here, and what are the telltale signs here? There is cold dust and there is warm dust. Okay. It's very significant because the cold dust is basically okay. How about the next one up? The one that has the visible image. That one, next one, that's too hard to look at. That one's nicer but not good enough. One that has more of a dark dust. Okay, right there. That's good enough. Perfect. The next one up. I should be doing this myself. Right there. Good. Excellent. Okay. So the warm dust does not always correspond to the cold dark dust. And the question becomes, why is this place that is bluer there and the stuff that is darker, why are they separate? Okay. Around this you have a lot of singly and doubly ionized hydrogen molecules. That's a lot of energy. To ionize one hydrogen molecule, you need a very high amount of energy. I mean, it's the smallest atom altogether, but to bump that electron up, it takes a lot of energy. And astronomers talk about photoionization and how these hot and heavy young stars are ionizing the interstellar hydrogen, and that creates this sort of red light that is emitted when the electron falls back into its base state. Okay. There's that. There's a cold dark dust that the WISE or infrared telescope sees right through. And then there are these embedded sources that always look goldish, bright and goldish in these sort of images. From my point of view, there is ion transport happening. That the warm dust is warm because of actual friction of the ions transported through the dusty medium. And note that some of the dust is not warm. It's cold. It's not being affected by this theoretical ion transport. It is being held in place, presumably by a magnetic field, and around it is this ion transport that produces the warmthness. And by warmth, it's not very warm. It's just several degrees Kelvins above the other stuff. Okay. Typically very, very bright in the 22 micron and 12 micron range. It was visible in the IRIS surveys of the 80s, and then it becomes resolved at high resolution in the WISE images. What you're seeing here is a WISE image at high resolution. And when astronomy got here and looked into the molecular cores where they expected to see the dust falling asleep and laying stars, they saw this other stuff. They saw a lot of filamentation. They saw these embedded cores that were related somehow, but were not blowing the molecular cloud apart.
So is ion transport just another word for current?
Well, you tell me.
It sounds like it.
Okay, so but see, it's you have to talk to a plasma physicist, because if I think that the magnetic field is present and the Planck polarization field suggests it is, it's moving these ions because they have a polarity, they have a charge across space, and it's bumping into the dust and it's warming the dust. Is that a current? Okay, you have to go back out to the ionized hydrogen as well and ask yourself, well, where's that energy coming from? And I have not resolved that problem. I need like an electrical engineering class or something. I want to hang out with more electricians, to put it bluntly, because I seem to have the parts in my head, but I cannot put them together. I cannot assemble them in a physically competent equation.
Well, there is something to be said here, just from looking at what you're talking about, if I could be inferring. If you had a situation where, for example, a group of particle in this dusty had a lot more ions, so it's generally more positive, but still could carry a current, but it wouldn't have to deal with as much current because it's ion heavy. So it would, because it's common misconception that in electricity we only count the electrons. It's just in metals the protons are unable to move. They're in a lattice. Yes. So all that move are electrons. So that's what makes it conductive and, obviously very easy. But in space, or if for example, a person gets hit with a lightning bolt, what happens is they get, you can get the movement of the protons as well in the other direction, because it's not so conductive. And obviously it causes, damage in the process. But in this case, you would have a situation where the proton's heavy, it would be proton heavy, it would be generally positive, but still has a current going through it, just like the other part does. But the other part happens to be lighter and has more electrons. So it becomes a positive-negative situation. They're kind of stuck together. But that's just a quick guess.
But quick as it is, how much further can we take it without real measurements?
Well, there you go. That's true. We could start by trying to figure out by making some general assumptions, and then there are certain rules that you could make based on the size of what you're looking at, and if we can get a decent measurement across a particular cross section and have a general idea how much area it is, then determine blah blah blah. But you're right; it would be based on a lot of spurious assumptions to start throwing into an electrical engineering formula.
Okay, so the good news is that any one place like this has a barrage of papers written about it. Star formation and the ISM has some special places where it's easiest to study, like the Perseus molecular cloud, or the Taurus molecular cloud, or the Orion complex. You can find...
What an odd term to use, molecular as opposed to ionic, but...
Well, astronomy is full of oxymorons and, how do you call this, outdated terms.
True.
They are not good astronomers, in the sense that the job of the astronomer is to name the astrum. An astronomer should be giving the name to the object in the sky that is best suited for it, so that other people can think about it clearly. And inasmuch as astronomers do not name their objects appropriately, but rather carry tradition forward, they are inhibiting their own thought processes and confusing other disciplines.
We have this conversation all the time. I am so happy to hear you say that about the way things are named and how confusing it is. And thank you very much for that. I appreciate that very much.
It really is. It's very clear to me, and it's a dire problem. So in astronomy, there's a lot of bad terms.
We were talking about this in reference to not just astronomy, but geology and many other things. So.
Yeah, so it falls over into many disciplines.
Well,
thank you for your.
It's about the a transfer of authority to a subsequent generation. Inheriting the terminology and the parlance is part of transferring authority from one generation of academic to another.
That's right. Thank you very much. If it was named according to function, then it would assign the function, and instead it's assigned to the finder of the function, so that you look at that person and not the object whose function has been named.
That's correct. So, science is not their objective. Most people who are in in position of social responsibility are there to wield authority. And it's the politics of authority that dominates the discourse of so-called science. See, science is a method not to fool yourself. To
ask questions of the universe, yeah. But mostly
to paraphrase Feynman, who wasn't that bright after all,
Ooh, harsh! Slam on Feynman.
Yeah. He said, it's a quality control for thinking.
In a way, yeah.
You can take quality control of thinking to any experience, any phenomenal experience. Anyways. This goes back to molecular clouds and the use of that. The problem is, if you want to get around the literature constructively, you've got to understand how they call that stuff, or you can't even go through the abstracts. And when you end up wanting to study any one of these places, you've got to go through 50, 60, 150 abstracts. In order to do that, you've got to understand what they're talking about. And in order to make, you got to know how they're talking about it, and then what their biases are, to understand why they're even treating the object in that way. So you have to drink some of their Kool-Aid to actually be able to extract the facts.
The nuggets of truth?
I've been building an immunity to iocane powder for the last few years.
Well, it's my
Slowly,
yes. Someone said something. It's even conceivable that we could teach a computer to go through the astrophysical literature, which is mushroomed in the past 30 years, and extract the facts and avoid the biases. And maybe
that's a goal.
Yeah, well, you'd have to use something like Wolfram Alpha, right?
I ironically know what that means.
Excuse me?
Or maybe,
I know what you mean.
Instead of bias, maybe the word rhetoric. If you take the rhetoric out of it, and that way, it because bias is automatically like a provocative word. So
No. I kind of think
well,
I think he's right though. It is bias. I mean, it's. We talk about this all the time.
So some things aren't intentionally biased or aren't trying to be biased.
Of
They're
course
just
not.
implications of maybe caused by causation, right?
I think a lot of it just comes with
it might
human
not be
social groups and interactions and groupthink and other things like that. I mean, it's totally innocent.
That's necessary to get to the to the stock of the soup. But when you take if you just want just the facts, you have to remove all the speculation that it goes with it, whether that's bias or not. You know what I mean? So rhetoric encompasses all the things also that aren't necessarily leaning in either direction, but maybe are just cutting the fat, just not necessary anyway.
So, okay. We have the situation of the rhetoric and or bias of the literature.
Sorry, we get off on tangents. It's part of the...
No, it's interesting. What has to happen is that astronomy has to hang cosmology from electromagnetism and see what falls off and what stays in.
That's true.
Right now, they hang the entire cosmological edifice off of gravitation and thermodynamics. Gravitation first, thermodynamics second, and electromagnetism is a consequence, right? And if you started from scratch and you hung it from electromagnetism as an exercise in non-biased understanding, what would actually hang and what would actually fall off, and how many things could we reinterpret from the point of view of electromagnetism and plasma? The caveat here is that we may not understand electricity as a whole. What we call electricity may be a truncated experience of energy in nature. You see?
Actually, I would agree.
Yeah,
right?
I'm an electrical engineering technologist, and I agree with your statement.
So
it's clearly the more to it. This predominant charge flow, the idea that there are charges that are not balanced in nature, something we're not used to on Earth. It's becoming quite obvious. Therefore, these are like what would be we consider in other times like just basically like mapping flowing rivers of stuff. Like that kind of holistic approach to it. If you can get down to the we're basically we didn't invent electricity. We simply learned how to harness it.
And we may tell me
encompassing not just one or the other. Goes with that bias too. It's like if we just hang it from electromagnetism and see what falls off, a lot's going to fall off. It's understanding each of the elements: gravitation, thermodynamics, nucleation. Like the EMF. All of it together, because it is all of it together.
Well, yeah,
it
their
might
relationship
very well
to each other,
be,
yeah.
Yeah, it might very well be polarized dust particles and this, that, and the other, but that's what we're seeing, right? And why they're acting that way. And all of that might very well be true. There's like more layers. The more we learn, the more layers. I have a hard time believing that it's all wrong, that way that they're seeing it. But I have a hard time believing that if it's all this one thing, then everything else will fall away.
Well, let's be fair. We don't think that they're wrong. We just have a different interpretation of the data. That's all. I mean, it's a matter of interpretation of theory. I don't want to be. I mean, these guys are doing good work, and they're helping mankind. I'm not going to be complete dicks to them. So
I can't do without them.
Yeah.
But on the other hand, when you pick up an astronomy paper, it really is quite formulaic.
Yes, they're hitting a wall. We know that.
Well, and I agree too that it's much more like let's figure out if this fits in our math rather than like observation based things. I think that it's really gotten away from acknowledging that maybe looking at something like a child who's never seen it before and then breaking it down in that sense, as opposed to somebody who's coming in with a bulk of information and they want to know how to apply that information to the thing that they're seeing.
Well, that's what happens in academia. Professors teach their graduate students to conform to their ways. And when you pick up the astronomy paper, the first thing that you read is a litany, and literally I mean that, a litany, which is the catechism. Here we're doing this because we know that this particular phenomena called by this well-known name has exhibited these phenomena that we believe to be so, and therefore I have the right to expound on this subject because I just told you that I adhere to your worldview. That's in every introduction in an astronomical paper is a statement that socially reads, I believe what you believe, and therefore I have the right to publish what I'm publishing. And then they go into what they're doing and how they're doing it and then what they found. And
Sir Fred Hoyle talked about this in one of those videos. I think it was called like Universe Cosmology Quest way back in the day. And he's sitting there and he said, the problem is the American graduate system, he said. It was that they are taught from the top down. And back in my day, this, of course, is a guy who was probably in school in the late 1800s, but not really, but you know what I mean? And he was saying that it was to thumb your nose at the professor was the way to get ahead, to prove him wrong.
Right.
That was the way. But now it's like, no, you proved me wrong, you're out.
Yes.
That's not the way now. It's basically the abandoning of science and the picking up of a institutional belief structure, whether they like it or not, in a way.
Well, okay, so that takes me to religiosity in science.
Love that term already.
Okay, so it's not just about the preservation of authority and influence. Religiosity talks about hope and faith are not a province of religion. Hope and faith are a characteristic of the mammalian consciousness. Meaning that, and we have such a limited horizon in time and space, that we have to have hope and faith to cope with our existence. You see, religion just leverages hope and faith to control the population. But in science, you really do have hope that you have faith that your colleague on your contiguous field is doing it right, and hope that it's going to hold in yours, in your field. When you're a hunter-gatherer, you really have faith that the sun's going to come up tomorrow, and you really have hope that in the following valley you are going to find the antelope, or you're not going to eat. So, hope and faith are not a province of spirituality or religion, mostly religion. They are a problem or a characteristic of like mammalian consciousness. And in astronomy and science in general, that is not recognized. They think because they usurped the throne of authority that religion had up until the 18th century, 18th, 19th century, that they're immune to it.
I was about to say that. No, you're right. Absolutely. 100%.
I have a question. What makes you present your debate or your idea as a mammalian consciousness type of thing? Because I've seen a lot of reptiles eagerly wait in anticipation for food for a long time, as well as other hunters hunting animals and reptiles. So
I can talk about myself and maybe some monkeys because they're that close, but I wouldn't want to like besmirch the image of reptiles. I just don't know. The form of my consciousness I can see more or less in a monkey, but I don't want to limit it to just mammals. I'm just thinking that.
Right. Well, my question comes from, a lot of a lot of people, we personify animals in different ways and things like that. And then we also like to think that human traits and human characteristic things that are just, we generalize for us, animals don't have them, or reptiles or other, when oftentimes I see the opposite, where birds are decorating their domicile for female birds, and there's beauty that goes into different things that we think sometimes beauty is a human attribute, or but things like what we're discussing here, I think that it might be cross phylum, you know, and there's certain ways to test, but I know for sure we can see a lot of hunters hoping and having faith that river is going to deliver that fish every day or every other day.
Well, I just didn't want to reduce it to material mathematical physicists. You know, mathematical physicists who are also materialists see the world the way,
almost by definition.
Yeah, almost by I just said mammalian consciousness because I want to make it applicable to all humans, except not isolate any one of them. You know, the plumbers versus.
Anyway, it's not important to your argument. I totally get that.
Yeah, not important. Sorry, I just wanted to make it. Yeah, you're good.
I mean, but you said something earlier that was just like, be true to your beliefs, and I will go. It was like Doctor Who, actually. I think the first Doctor, William Hartnell, said something very similar to that about, and I will have faith, you know, that you will go in the belief of yours, or something like that. And it's
faith and hope.
Yeah, faith and it's very true. That it's something that, as much as I would like to say that I'm very cognizant of my own biases and try very hard to remove them, always, like just hunt them down and kill them if I can. It doesn't mean that I'm not above having faith that that I can figure something out, even, or that I can work through a problem, or I can find the answer. And there's so even those type of faiths and beliefs exist.
It's intrinsic to consciousness. We cannot have an individual consciousness without going through
until you hit the state of nirvana, apparently, and then climb to the top of a mountain. Then you're good. But until then,
the problem is that scientists are not good psychologists.
No.
Astronomers and astrophysicists don't look at their own practice expecting to find projections and errors of faith and hope.
The institutions themselves were made before the advent of psychology.
That's correct.
I mean, that alone should tell you that they weren't prepared for this.
Yeah, well, but modern people, or modern cultured people, should be both mathematically able, physically inclined, and psychologically savvy, right?
I would agree generally.
You'd have to, but that's a culture with a big C, right?
Mm-hmm.
But it all comes down to the fact that astronomy and astrophysics doesn't matter. What happens in the next star or the next galaxy over really doesn't matter. It doesn't affect the bottom line. It doesn't affect your mortgage payments. It doesn't affect your reproductive success.
So it allows bias to creep in because...
Correct. And to stay in.
You can't... I mean, just as an example, there's a purity that some might say, a practicality, a pure purpose to electrical engineering. Because it does exactly what these numbers say it's going to do. I can, if I build it right and I do everything right, I know that I'm going to have a 1.5 voltage drop across this diode. Know exactly how many atoms I put into there and doped it with. I know exactly what I'm looking at. That type of knowledge translated into what we're looking at here in space, to me, that nothing could overstate the benefits to mankind, at least in understanding astrophysics. However, that would completely challenge those already in power in astrophysics.
Yeah.
So of course they would be against it. That does matter to them, yeah, because that's where funding goes.
Grant or
we don't care about that. So, I mean, I certainly don't care about that money. I'm not doing it for the money. I'll tell you that. I'm certainly not doing it for the fame, and I'm not doing it for the women. So,
well, but big science allows single ideas to go much further, right? Big science also tends to solidify its course and understanding. You're not going to spend $2 billion in some program and then come up and say, no, I was totally wrong to begin with.
That would actually be an advance in many cases if you could
but it doesn't happen.
I know. They only start looking for what they know is going to be there, and the course is laid out in front of them like a train track. They can't change it. So
the problem is not scientific in a strict sense of the word. It's not scientific in a popular notion of the term. It's sociological and psychological and economic, and it's all of it. And it's hard for the people inside to recognize it.
Well, yeah, you're trapped in a. I mean, you need to literally sit back and do what would be like something like what Noam Chomsky did to the media and the government, so to speak, in Manufacturing Consent in 1993.
Right.
That sort of institutional analysis where you look at all the factors, what is influencing people's decisions. That type of map would give you a handle on what you're looking at. I can envision what it would look like as a flowchart type of thing. But I certainly don't know it all, but I could see that there's some big friggin' loops, feed themselves.
All you need is a flowchart, because ultimately what you need is an algorithmic approach to science. If I assume that it's electromagnetism and I look at a star, then if.
That's how I generally see things. I mean, don't get me wrong. Gravity must play a role, but I don't understand now with this whole new thing. And if you begin to chase Einstein out of the equation, then you're left with electromagnetic interpretation of gravity. But we don't have that hammered out. We don't know what that means. So that's
someone does.
Well, we can infer, but we don't really know a formula for going, okay, this much coulombs on the surface of a surface with this many cubic meters, square meters equals this much gravity. The gravitational constant is thus. We don't have that worked out.
I don't have an answer to that either. I'm not qualified to even start at that, but I can tell you that anti-gravity craft seem to be all over the place. And someone's gone anti-gravity craft and electromagnetic propulsion or something.
That wouldn't surprise me. No, that's there's many ideas with regards to how that could function, and I recognize that. Just thinking about it purely, understanding that the ground is this polarity and the ionosphere is this polarity, you could theoretically arrange it if you had plates of the correct size, figuring to go up and down, and how you do that. I'm sure this is what Tesla was thinking about when he began to realize that too. And I don't mean to, claim to know what he was thinking. I just mean, it would just come to mind.
Well, I've seen presentations of aeronautical engineers talking about electrogravitic craft that were created in the 60s through the 80s by the U.S. Air Force. And they present these monocrystalline, what do you call these? Quartz layered, copper and quartz layers of the base foundation. I'll try to point you in that direction, but
that guy who used the beetle wings. He was at the turn of the last century, but he made that little levitation craft that from the backs of beetle wings.
Well, that's not a bad point, because the structure in the back of beetle wings are at nanometer scale, nanometers, and the dust out there in the galaxy is at nanometer scales. The whole gravitational dynamic of the galaxy may hinge on exactly the scale of that dust out there. Like the magnetic. Tell me.
Go ahead. Well, I was curious. You said that the shell is based off of nano scale. I'm curious on the human, what type of nanoscale stuff and the nano dust might interact as well.
Well, there you have to get into cell membranes. Okay, so boy, I mean, in the human form, at that scale, you have to arrive at something called the epigenome. That is, all the little molecules that float around inside the cell and interact with the chromosomes. It's not just the RNA and the DNA or the messenger RNA. There are all these other atoms that tend to bind and relate to the genome and rules or regulates the expression of the genetics. And you can go back out to the cell membrane, and also you find receptors on cell membranes at that scale. But that's an entirely different world, much more complex and varied than what you see or what we know exists out in the interstellar medium. Like, it works at our scale. We can relay information across the body and the nervous system effectively and efficiently enough to have consciousness. Like, we have all of these interactions that happen in our body that yield somehow the epiphenomena of consciousness. At a galactic scale, we don't have that. We don't know if the galaxy is conscious. We don't, I want to think of it as a living organism, like a huge plasma whale. That's how I want to think about a galaxy, but that's kind of far-fetched.
Well, I see a little possibility that it could be part of something. It could just be like a functioning dendrite, but because just thinking about it, you'd have two currents going in opposite directions through what would be the galaxy. They would be sort of pinched down by the magnetic field, the load that would be there, all of the surfaces of all the things that would represent a resistance. That would be part of the equation. The other part of the equation would be the magnetic resistance, sort of induction, and all the little loads that are running through that. And then there'd be a capacitive resistance. We were talking about doping earlier. That would basically make it sort of have a direction. Like there would be more in one direction than the other, so there would be a voltage drop across the galaxy. If you're just looking at it just simply as a motor, and how it would work, and that this is kind of from that point of view, it makes you wonder the characteristics. What makes that different than a quasar? What is that we're looking at right there? I mean, is this, there's so much this lens of the sort of plasma cosmology, electrical universe sort of point of view does not grant infinite knowledge or something. It's not magical.
No.
It's just basically saying, look, electromagnetism probably has something to do with what we're looking at here. If you just say it like that, you're not, I mean, it implies so much. Like, come on.
From my point of view, the most interesting thing is that plasma tends to behave in similar ways, a great variety of scales.
True.
And that it's able to transmit information and energy across space. And as such, it presents a unified, it unifies the cosmos. if the electrical or / plasma activity at the molecular scale in human cells and organs is responsible for life and consciousness, and the same forces are responsible for creating galaxies and stars, then we do have a principle to unify the big and the small, the material and maybe even the spiritual. And I think that's the most not revolutionary, but liberating effect of adopting a electrical or plasma cosmology perspective. That you can suddenly recognize a vital principle to the cosmos. That is, the replication and transmission of information becomes the definition of life. And the mediating force for this is plasma and electromagnetism, or the plasmonic conduction of energy, or something like that. And then the question becomes, well, if the galaxy is a plasma body itself, does it have any consciousness? And then let me present another important point, is that the dominant structure in the universe is galaxy, not star or planet. Stars are much further apart from each other relative to their diameter than galaxies are apart from each other relative to their diameter. So if galaxies are the dominant life form, then this really is a primitive universe. Galaxies have not evolved to become self-aware, but we have. Some early precursor of a universal consciousness. And this to me all falls out of electromagnetism and plasma being the mediating force and activity between the tiny and the very large, between the tiny and the tiny, between the large and the tiny, that kind of thing. I think that's a useful idea.
I have a question for you. Huh?
Go ahead, Eugene.
Yeah, I've had a question for you relating to these, I don't know what you call them, these, transient discharges that you've detected in the images. So are they even recognized by like mainstream astronomers? Do they have a name?
Okay, so the closest...
Can you tell a little bit about them?
The closest thing we have is light echoes. Okay? Like, let me give you an example. I worked, what happened is that mainstream astronomy has not applied blink comparison to the ISM. They just don't even think about it. It does not cross their horizon. What they do recognize is something called light echoes. And they see, and I could probably bring up some of that right now because I actually found some of that lately. The other thing that they recognize is gamma ray bursts, right?
Right.
And now, because of the Gaia results, they're talking about blue transients. Okay. What they don't talk about is filamentary objects, light. Well, what to be the proper term for that? Luminous filamentary transients. What I'm calling, that's plasma discharge. Gosh, look at it there.
We're just watching lightning discharging in slow motion is what we're looking at.
Well, yeah, basically.
Those
what
little
happens
sparks you see, along the chain occasionally,
Well, that's what I believe. That what I'm looking at is just little sparks out in the galaxy. The galaxy churns and churns, and here and there it goes. It gives off these little sparks. Some of them are accompanied by high energy outbursts as well, and those became relevant in the 20th century. But not because they were looking for them. They were relevant in the 20th century because the gamma ray bursts were being monitored to ensure the compliance to non-proliferation nuclear treaties. Like they had satellites in orbit looking for nuclear explosions because they give off gamma ray bursts, and then they realized the gamma ray bursts were coming from the sky, and that's how they discovered gamma ray bursts, right? Seriously.
No, it's just funny. It is just humorous.
It is.
There's also a phenomenon called terrestrial gamma ray flash that the lightning on Earth basically produces gamma rays.
Right. So my contention is that many of the unattributed gamma ray bursts or bursts that haven't been associated with a specific galaxy or extragalactic object actually belong in the interstellar medium. That a lot of this stuff happens in the interstellar medium and they're not expecting it, so they go around looking for some high-density object near the location of the gamma ray burst, and then they go, oh, it's this galaxy. Or, they pinpoint the gamma ray burst, and there's always going to be some galaxy down there, The more you look, the more galaxies you find.
Exactly.
Right? So because they're expecting this to come only from high-density objects, like high mass objects, and they say, oh, it's a gamma ray burst coming from the galactic core of this galaxy. And, the fudge is, instrumental error or something. The kicker came a few years ago when they started observing M stars, which are very small stars, cool red stars, small cool red stars with high proper motion. These were giving off gamma ray bursts, and that they could not understand this at all. And I don't think it's just one of the things that they go, oh, we never expected this, and never happens. And they never look at it again.
That happens a lot.
Yeah, that happens a lot, right? So, gosh.
Just go ahead.
So what do you think causes them? Is that like, I don't know, for example, if you observe a sudden appearance of a filamentary structure, so it probably means that the plasma was there anyway, it just wasn't bright before,
That's correct.
Right?
That's correct.
So something has lit it up, so to speak. Right?
Yes, so when you look at these molecular clouds carefully, you realize that there is a web of filaments there.
Correct.
Right? And then once in a while, you see some of these light up. It's just kind of luck of the draw. And whether that particular one generated gamma ray burst or not, I don't know. We just it doesn't. We might never know. In the sense that getting all those instruments pointing in the right direction at the right time to catch the thing, the closest thing we have that is the SWIFT satellite. And the SWIFT satellite was put up here to deal with gamma ray bursts, and it has an X-ray telescope and a gamma ray telescope and an optical telescope. And it may swing to catch the gamma ray burst and see what else it can find. I have not been through the SWIFT results, but that's the well for multi-instrumental, multi-bandwidth studies of these energetic outbursts.
Dave had some information indicating that these outbursts had patterns to them, that they were something you could see sort of going across the sky in some cases.
The whole sky?
Well, this is the information that he was presented with. I'm sure that it was a paper on something.
There was a paper that basically stated that there is some ordering of the positions of gamma ray bursts in the sky. But it was, well, at least to me, it looked pretty, I don't know, esoteric, if you like.
Or spurious. I wasn't sure about either.
Yeah, I wouldn't trust the author, basically. But who knows?
Okay. So one of the things that I did was study the results of the ROTC experiment. ROTC was a rapid optical transient search. It was the original response of academic astronomy to gamma ray bursts. And they had 4 little robotic telescopes around the planet, and they would swing to catch the gamma ray burst detected by the Compton Gamma Ray Observatory in space. And what I found was that there was always something wiggling near the area of the gamma ray burst. The ROTC located the gamma ray burst. Sometimes it found a optical transient, and when I did the blink comparison, I half the time found something that looked like, oh, this is the kind of stuff I've seen elsewhere light up, kind of thing. And I never got down to the statistics of it, but my impression was that there's always something wiggling in the interstellar medium. It's no, I can't assure that the wiggling of the interstellar medium is definitely associated with the gamma ray burst, because there's so much wiggling of the interstellar medium as it is. No matter where I look, something's going to wiggle. I can't exclude the fact that it's a arbitrary or line of sight sort of connection. But let me see if I can. What did I have last night? Maybe I can share my screen. I opened. Yeah, let me just get something here in place.
It's interesting that we could be seeing a spark that is sort of like across the, shall we say, the border between the galaxy or star and the interstellar or intergalactic medium. It's something that should appear actually occasionally. Like, I mean, these things are not perfect. Just like the sun has areas that have sunspots, these places should have places where the field either breaks down or has a minor short and they just spark for a second. But overall, will rebalance, because once you drained off a bit of that power in that flash, the boundary then reconstitutes itself because there's not enough potential in that area to keep it going. And it sort of self-corrects, the self-organization principle of plasma, as it were.
Boy, man. Yeah. Okay. So let me just. I'm scrolling through stuff here. Now I gotta do something with. Not that. Not this. So it's not. I have too many computers. Is what it amounts to. But I do have something open here. How do I share my screen here?
There's like two little squares.
Got it.
You have to actually fight Heather in a rap battle.
Uh-huh.
I'm pretty good. You better, just so you know.
Laying down the track.
Fair warning.
That looks pretty amazing.
There we go.
You see it?
Yeah.
Okay, so let me turn off the IR. Now, okay. This is, okay. Can you see it blink?
I do.
Okay, so this is a little nook in a place called SH-155, which is a very useful catalog to study dark objects with. This is fairly low resolution. I think it's like 2 arc seconds per pixel or something like that. And this object is not supposed to be there.
But I do see it, though. It's there.
You do see it, right?
Yeah, I do.
And you gotta tell me what it is. Why is it there? Why is it also accompanying this change of ionization in this particular dark spot in this nebula?
Is it like a Jacob's ladder?
It's
Jacob's ladder?
Well, actually, it's a continuous discharge. It looks like a discharge all the way through, going from much larger than, I mean, it seems to be the distance that it's going is larger than this actual screen, because you can see this other part lights up in accordance with it. But, I don't know where the beginning and end is.
The thing with this particular nook in space is that also you find X-ray sources. You find HH objects here. This is a very energetic place. which is totally the opposite of what star formation would tell you, is that these are quiet, cold, dark places where stars can gravitationally collapse and they radiate their heat and somehow they overcome the angular momentum and then they become stars, but only big stars, because small stars, they can't be done. But instead you get all these different changes, all of these different sources in higher energy band passes, and you'll see.
I was going to say, slow down there, Eddington.
And you see flashes like you see right now. That's the typical. Tell me?
Can you please tell what you are changing when you? Is that the same frame taken at different times? Or
this is the 1993 exposure, and this is the 1956 exposure. So 1956, 1993, 1956, 1993.
So it disappears rather than appears. Is that correct?
Well, it disappears rather than it appears. There tends to be more of these objects in the earlier survey, which is a problem. Okay, when you go down a list, a heuristic of is this contamination during exposure? Is this a shadow on the emulsion? Is this contamination during the processing? Is this inspection damage? Okay, the earlier plates were of much more interest to the astronomies of that era, and they were inspected more often. Is this a scratch in the emulsion? Okay, so you do find them in the newer survey, and and you do find them in the blue surveys. You tend to find them more in the red surveys because the red surveys took 40 minutes to expose. But the blue survey took like 7 minutes to expose because the emulsion was much more sensitive to blue light than to red light. Well, the fact that you find them much in a greater proportion in the red plates, I think is related to the fact that the red exposures were open for that much more longer. So you tend to find more of them. I think that's what the probability of that looks like. The difficulty is that the red plates were inspected more often, and you have to worry about inspection damage. Okay. Often, let me blink this for a moment. I think there was something here. Right. So here you have appearances or disappearances of these things, and these things over here, and these things over here. There's going to be probably an infrared source, which is right here, connected with that. And the little piece, what do you mean there's a star forming in this particular knot of dark stuff? There's not enough mass there to form a star, but yet there's a protostellar object right there. They're not really impressive. There are some that are more impressive, though. I have to go. I didn't prepare extremely well for this.
What is that light blue object?
I don't know.
What is that?
I literally don't know.
Well, that looks like it's being ejected right out of that star.
Yeah, there's like a little blur next to the left, too.
Yeah, well, the little stuff to the left, it looks like a blue transient to me. This big thing, it's not like I have not seen stuff like that.
There's another one below it, too, to the right, on the bottom, right below your arrow there, and just to underneath a bit.
Yeah, this I don't.
It's shooting a space tornado at us.
It's a smoke ring.
When you go around, so the process of doing this involves like equalizing the contrast. I can't get into that amount of detail. Wait. Because in order to get here, you have to process the data to a point where you can blink it effectively, and they're analog surveys, so you need to bring the base, not the base, the bottom of the histogram has to be equalized so that you minimize the differences between the emulsions.
Okay.
And then you can blink for comparison. Basically, that's what I should have said. Once you minimize the difference between the emotions, what drops out is the stuff that's really, really changed. Where? Too many things open. Ultra, Herschel, CO2. Now, I kind of don't want to go through all of it. No, it is. Got a bunch of stuff open here. There's nothing there. That's Herschel. That's radio. It's Galactic Center. Crypto. Sorry, I'm actually looking for something. Those guys died. That's another story altogether. Here it is. Right? That's IR. These out. Right there. Okay. You see this blue streak over here?
I do.
That blue streak it disappears. And it's one of those things that I would say, that doesn't belong there. That could be a light echo. This stuff over here, that's plate damage over
Gotcha.
here. That is probably a transient. I don't know what this is. I really don't know what that is. It's not there, and it's not there. This particular...
Are these images taken from Earth? Or?
Yes. These were images taken by the 48-inch Schmidt camera on Mount Palomar. It's a Palomar All-Sky Survey that later became the Digitide Sky Survey. And they did 2 sets of these, one in the early and mid-50s and one in the early and mid-90s. And in the 50s, they took the blue and the red plates contiguous in time. In the 1990s, they took the blue and the red plates or exposures as far apart in time as was practical, so they could get 3 proper motion data points. What I have learned to do is combine the WISE survey with the DSS in such a way that you can actually witness both of them together. So here you have all of this warm ionic transfer happening. That would be the full place. Let me turn that off. And you can also see the protostellar embedded point sources here in this golden down here. And if you're lucky, these are near-infrared sources. So this particular example is interesting because you see all kinds of stuff. You see stuff that's clearly contamination. You see stuff that is light that's in the exposure. And you see stuff like this that you just wonder what the hell it is. I mean, I just don't know what that is. And I've seen a lot of it.
It just appears out of nowhere.
Yeah, and so here there's some more changes in the ionization. Let me turn that off. I'm turning off the near-infrared point sources, of which there are plenty more to see than the visible. Here you see a change in the ionization. And that red stuff over here, that just really is a change. So there is a topic in astronomy called variable nebulae. And variable nebulas is what astronomers call places that look different from epoch to epoch. Some of these variable nebulae will be visited by plasma discharge. One of the best places to look at this is called VP. Oh, is it VP Cepheus? VP Cepheus, I think. It's a cataclysmic variable star surrounded by a dust cloud that also has like this giant tether that can be seen in the mid-infrared. And if you photograph that place long enough, you will get a lightning strike. And that was why I bought the equipment I did to carry out that experiment, to monitor places like that, which I knew were active.
Places that occasionally spark.
Yeah, exactly.
And we know this happens because I watched Wrath of Khan, and then when they went in there, you could see the lightning. Yeah, it's true.
Well, I mean...
No, I'm just kidding, but still, the truth is that they must be there. I mean, naturally.
They must be there.
Yeah.
And you know, things happen on an energetic continuum. If we understand electricity to be a foundation for natural phenomena, whether it be at the micro or the macro scale, and you're already capturing all these gamma ray bursts, those gamma ray bursts belong to a continuum of energy that is going to display luminosity or great magnetism from any given perspective. You see? Once you recognize that the universe is founded upon electromagnetism, or what we call electromagnetism happens to be the foundation of nature, and you get these energetic events that seem to be connected to nothing, they're going to be connected to electromagnetic events. And where's the charge coming from? It's coming from the capacitance of those clouds. How is it those clouds capacitating themselves? Well, they're carrying charge between the grains of dust that happen to be, it's like semiconductors. They've got a shell of water around them, and they've got a core of silicate, and they're interacting among themselves in a context, the galaxy, that is also visited by this huge electromagnetic field that can be seen in the Planck polarization data. You see?
Oh, yes.
But it seems to be a cascading effect. If you put a M-dwarf star moving at high velocities through one of these regions of space that's dusty, well, maybe you do get a plasma discharge from one star to the next. Eugene, what I should do is, with some more time, is prepare a short list or a short series of the most significant phenomena found. And there's plenty of it. There's so much of it that I just literally am too daft to go through the whole list. But
what you sound so far.
That sounds just great. But I also have another question for you. Have you looked at the immediate neighborhood of the solar system? Are there any interesting structures there, like at nearby stars such as Alpha Centauri or Sirius or whatever? Have you looked into
Yeah, I have. Let's go to that. Let me find Galaxy Explorer in one of these.
And while you're looking that up, I'll just explain something that hopefully this makes sense. We're dealing with such large amounts of space that if you start thinking about the influence of the sun, just our sun, and then you think about that there's, let's say, 3 or so electrons and or protons per cubic meter out there, and then think about the amount of space there is between us and just the next star, and then try to put that into an area. And then you're beginning to understand the sheer amount of current that there is flowing. And this is, it's not always, it's constructive as well as destructive in the way that it functions because of this. It's the right-hand rule nature with magnetism that makes everything just have this special, as Langmuir said, the plasma property of the self-organization principle type of thing.
Self-similar and self-organized. Okay. The thing to understand here is that this stripe that runs sinusoidally through the image is the plane of the solar system. You're looking at a presentation of the IRIS infrared data.
Is
Right.
that the zodiacal light?
Well, no, they're not the zodiacal lights. They tried to remove the zodiacal lights from the data set. That's why the data set is scarred. Okay? The zodiacal lights are very, very, very important because maybe the charge that feeds the sun is not coming into the sun's poles. It's coming onto the whole plane of the solar system via the solar system plane dust.
You mean
AKA
along the equator?
Yes, correct.
Well, in actuality, and this is important to note in electrical engineering, it's both. They're flowing in both directions because you're going to have flows that are going in one direction and flows that are going in the other of ions. And so they're literally doing the exact same thing, just in opposite. And so you're 100% right. There should be counterflows, and I think that I think if we look at this, I mean, there's predominant direction of the current that's feeding the sun. I mean, there has to be. It seems to be coming more from the south than it is from the north. But other than that, that's what we're looking at for that gives us polarity. That gives us a magnetic structure, which of course creates the bubble, which gives us, of course, some extra structure to the large electric field the sun has, which seems to be pushing out to the heliopause, and that's where that connects to this current, I guess, as we and Jim and I and others have discussed. It's
right.
How this might work. So,
what I do not see is a trace in the interstellar medium that I can associate with the sun itself. That is, that the surveys that we have to date, are not smooth or fine enough to pick out whatever is feeding the solar system in the dust. The long IR into the radio should pick up all the dust. And maybe we can, in the future, we'll have more sensitive surveys, but up to now, when you look around the whole sky, because this is a Mercator projection of the whole sky, you don't see it. Or if it is, it's really hard to recognize. And I have made an effort to recognize it. And it's not, it's very difficult. What you do end up seeing are tendrils that might connect the galaxy to other galaxies. And I think that's really important. And that you can kind of make out if you know what you're looking for. This is actually maybe not in this projection.
Are these coordinates there on the screen galactic? Or
Galactic.
Are those
Galactic, yeah.
So,
the cursor is a galactic.
So I'm just curious about the solar apex where the solar system is moving. Can you find it? It's 56 longitude and 22 latitude.
In galactic?
Yes, 56 longitude and 22 latitude.
Okay, I'm gonna get it somewhere else. Hold on. What I'm actually doing here is getting a better source, which is Aladdin Light, which is from the Europeans, from ESA. I'm going to take a coordinate now.
Yeah, it's 56, 22.5. Let's say.
Okay. And the longitude and the latitude?
22.5 degrees.
Okay. Let's go through this first. That's Akari, the Japanese infrared probe, looking at a 10, basically 11 degree field. There's not a lot of detail there, and it's a very good probe. Here's all wide, which is not presented very well. This is the same stuff we were looking at before, the IRIS data set. Not a very high resolution. Pan-STAR might have something for us. Pan-STAR does not pick up dust.
Wow, it's pretty deep.
Yeah, but it's pretty deep. That's what I like about Pan-STAR. It's very deep, but it's near infrared, basically. The Mellinger is going to give you what it looks like in wide field. I mean, if you put your DSLR out there and pointed it this way, you'd get something like this. You get something like the Mellinger. The DSS2 we're used to, but you know what? It's not.
Where are we looking?
We're looking at Eugene.
It's the solar apex, where the sun is moving with respect to the local stars. But I think there's nothing interesting there.
That's correct. But it's such an important question. I'd rather demonstrate it.
Well,
you know what I mean?
I would think, and I could be, of course, completely wrong, but it doesn't seem that the heliopause of the solar system is homogeneous or circular or anything like that, which seems to imply that if it does have a magnetic field, it should be bent just like the magnetic field of the Earth is bent, and therefore the apex of the Earth is not necessarily the most awesome spot. The actual connection is sort of more towards the sun, if you know what I mean. The whole, I guess, of the magnetic donut sort of bends in that direction. But
gosh, I remember seeing an article in Science not long ago, and they presented an image of the solar. It looked more like it was like this, like the magnetic field of the solar system was shaped a little bit like that. Do you remember that at all?
Yeah, I saw that. Definitely.
Yeah, you remember that?
I do remember seeing something along those lines.
Yeah, it was one of the covers of Science, I think, and I have not followed up, but I said, "Oh, look, it looks like a little baby." But it had like magnetic lines. You know how they like to represent the magnetic lines, like they were physical things.
Of course.
Yeah, and so I remember that, but what else?
Still crazy.
Yeah.
I mean, and look at the awesome magnitude of the filaments that you're looking at just in this image here.
Yeah.
And this is just basically getting a look at our galaxy, a bit more or less.
Yes, that's correct. This, I mentioned this earlier. Maybe I haven't. This here is the Earth's molecular cloud. It's this one filament that goes all the way up to here, right? Well, if you go really close, these two big sources are M81 and M82. That's what these two IR sources are. And the question that I would like to answer is, does this cloud of stuff go all the way from our galaxy to M81 and M82? You see?
It appears.
Well, astronomers will tell you it's a line of sight thing, but it's not connected, right? But I think it's a really important question. And it's not the only one of these.
And we wondered if they're like baby galaxies themselves. Like, aren't they weird? Like M81 and M82?
M82 is a weird galaxy in as much as it looks like it's blowing itself apart.
There is a hypothesis that recently, like 70,000 years ago or so, there was a more or less close approach to the solar system of other star which is pretty small. It's called the Schultz star, and it's of the M type, I think.
Mm-hmm.
So it's like, again, it's like brown dwarf or red dwarf or something like that.
It's the M star for the smallest and the main sequence.
Yeah. So what is interesting is that at the time of its closest approach, it was somewhere in that area around the M81 and 82, around the handle of the Dipper, Big Dipper. So yeah. The solar system seems to be a very strange planetary system because it has rocky planets on the inside and gas giants on the outside. And there's this idea of a stellar merger. I found that fascinating.
Well, a la Saturn stuff, Velikovsky and such.
Well, yeah, you see, the hardest problem of the EU, from my point of view, is its adamant adherence to Velikovsky catastrophism. And that is, it's brilliant for Velikovsky to have diagnosed the trauma of humanity. I think that's a brilliant thing to do. But it's very hard to bring that into hard science.
Certainly. That's the argument between basic plasma cosmology. Plasma cosmology is what we're talking about here, more or less. Plasma astrophysics, that kind of nature. Yeah. And the electric universe does have this other connection with Velikovsky. And there's no doubt, if nothing else, we can skip necessarily, because I've seen discussions that didn't require, like, for example, Rensburg. I can't never pronounce his last name correctly, but
von der Sluis.
Thank you.
We should have had Ido.
We should have, but but he's proposed a version that did not require any planetary rearranging. But you're right. There is a connection to that. There's definitely but there is a bit of a homage there. We shouldn't necessarily skip out on what this academic retelling might provide us with information. I don't want to cut that off. There's some useful information to look, if we take the past as literal, in regards to some of these myths, is what I mean.
Well, we are a species with amnesia. We do know that the Younger Dryas, the end of the last ice age, was a cataclysmic situation on this planet, even though the geologists and the climatologists still don't want to quite face it. We do live on the surface of a rocky planet with a very thin atmosphere, believe it or not. Catastrophism and punctuated evolution have plenty of evidence in the biological record or geobiological record. Faith and hope force us to not look at catastrophes. It's like, it's too much.
Well, we write them out of history sometimes.
Well, yeah, and we forget them, and it's too much for us to know that we could be destroyed at any moment. Because we live under 3 kilometers of atmosphere at most, right?
Thank God it's there, but that's...
But it's not a lot.
It's not a lot, no.
And the World War I saw a lot of tunnel digging. World War II had a lot of bunker building, and it has not stopped from the mid-20th century forward. Once the space age became a reality in the mind of engineers, they came to the conclusion that the only sensible place to live was under a mile of dirt. because it's not safe to
plan.
live on the surface of this planet. It simply isn't. Whether because of nuclear holocaust or because, in fact, we could be derailed by any number of high-energy events that come from our galaxy, from our interstellar medium, interstellar context.
But as a whole, I'm just saying I appreciate necessarily what you're saying, but there is clearly, I think I'm happy that they were there, and I don't want to necessarily stop anybody who wants to, because it's beyond my talents to go and start piecing together old Hebrew manuscripts in the correct context for understanding catastrophes. Not something I'm going to be able to do. There are people whom I trust to do that, and I will. And I can look at them and look at their evidence and compare them to each other, because that's all I can do as someone who's not an expert on any of that. I use that inference that they give me some sort of intellectual weight to make some geological claims, especially with regards to catastrophes and the blowing of material off planets. But most of that comes with an understanding of electricity, in my opinion. But there's some merit to understanding it from a catastrophe, or at least having a verbal record saying, "Hey, guess what happened? This, and it was bad." Type of attitude towards it. Because those tales are ubiquitous. We can't. Ignoring them seems silly at this point.
Okay, well, I think this whole chapter of the conversation is related to the difficulty of changing the mindset of mainstream astronomy and astrophysics.
Oh, well, that's true.
Right? And at the same time, hold a catastrophic and Lacockian view of history. You see, those don't travel well.
No.
And that's a socio-political dilemma. You want to be, or some people want to be very faithful to the lights that led them forward, and other people just want to get down to expressing how gravity and electromagnetism are related.
I'm more in. I think the other will just come naturally. It would become something that, where do we go from here now that we've all adopted plasma cosmology? Well, we should probably start looking at the other sciences. I just know that other people are going to jump ahead anyway. But I'm just, because they're already there. They're already doing research in their own way. But you're right. In the general scheme of things, we should probably stick with the plasma cosmology to talk to people in the astrophysical realm. That's the only way to be practical.
Yeah, you can venture into catastrophism and go into the geological record and even the cultural examples that we have, but I don't want to self-censor
anybody on this particular
format
all right, in that sense, but don't worry about it. I understand. We understand. We're all together. So
okay. This is data that okay. So this is high end. It doesn't get any better data. Straight from the space telescopes, Certif and WISE data, and this is what it does. What I've done is treat it so that it's in the same register of colors. Gotcha. Again, trying to minimize the differences between the data sets so that they're would otherwise be the same, except something changed, right? What you see in the middle is Cassiopeia A, which is about 3.2 thousand parsecs away. This stuff is a little bit closer, but look at it change over a very short amount of time. We're talking about like 6 years difference between one and the other. And, look at this stuff over here. On this side over here. That's more recent, less recent. More recent, less recent. So is this a cloud of something that's receding into space at that velocity? Is that energy, electricity moving through space that's can be seen to be moving at the speed of light or something like that? That's really what we're looking at. So instead of being sourced out of these old emulsion, glass plate emulsions, very high tech for their time, kind of not current. These are sourced from space telescopes and present the morphology of interstellar morphology of electrical discharge. I mean, you might see a shape like that wiggling off of the opening of some high voltage circuit in some transformer, farm somewhere.
It came to mind.
It came to mind, right?
Yeah.
And this is taken by very high-end space telescopes. And so, I mean, that's what we have to work with. I mean, it doesn't get any better than this. Now, how do we attribute that to an electrical current or to a, quote, light echo? What I can do now that I couldn't do before was to pin down the distance to the molecular clouds involved by using the Gaia parallax data on embedded sources. That is, embedded stars that are clearly associated with the molecular cloud and have Gaia parallaxes can pin down the distance to those active regions. In this case, this particular active region, right? So with that physical parameter pinned down and a luminosity derived aperture, photometry, then you have an amount of energy. And then you have to think about, well, is it possible to do it physically? Just because you have to live in their house before you can move out, right?
True.
And so that's something that I wanted to really, I'm not dreaming this up, but the record in the Palomar surveys are open to question. Some of them, other ones are not. The best ones look just like this in the sense that they're that convincing. But once I got a hold of this data, I was like, okay, now this is something really different, really important happening. And so that's the end of my presentation. Ta-da!
Well done.
Yeah, that was pretty amazing, actually.
Yeah.
Yeah.
Thank you.
Very, very convincing that we'd be looking at especially I love the overtime. I mean, it's just so slow to, watch a discharge between stars and or other parts of galaxies and so forth, and looking at it as a transient event, and not being able to tell because you're looking at this part of the sky it's just not moving to you.
Yeah.
And it's understandable, and we're coming to the conclusion, I hope. I mean, we've noticed this with the Great Red Spot. The telescopes that are looking at it now are seeing that it's like much smaller than it was in 84 and 70 something. Yeah. And going to looking at how small or how much larger it was to the telescopes in the 1700s, when they said it was just a huge sausage type thing that was across the surface. Yeah. That's on a planetary scale, let alone we're talking interplanetary and/or galactic.
Well, so the study of the solar system from an electrical dynamics is much more promising than the interstellar medium stuff. Just the rings of Saturn and trying to explain why the shepherd moons don't destroy the rings of Saturn altogether. How to explain the attenuation of the oscillations introduced by the closed passage of a shepherd moon in the F ring of Saturn. Or is it the E ring? No, it's the F ring. That question alone should stop any scientist in his track thinking, okay, well, I got gravity and I got EM. What do you think? Gravity by itself would destroy the ring. EM, well, maybe that's attenuating the stuff. But people don't think clearly. Science doesn't want to progress.